Okay, so in a way, looking back at what we did in the last 2 weeks, we can think of the second component of the course as differential privacy for statisticians. Right? We looked at data, and we didn't do the complex things we're used to do these days in machine learning, train models, etc. We did the basic stuff. So the first week was the most basic thing you can do in statistics, I think, which is estimating either a moment. We focused on the mean and a little bit of the variance, the second moment, and quantile. Right? We focused on the median, or sometimes the quantile we wanted in order to truncate. And then the next week we moved on to somewhat more complicated statistics, such as the difference between two averages and things like that. And we used it also as a baseline to discuss the subtlety of local sensitivity, smooth sensitivity, etc. Okay. This week we will move on to do probably the next simplest thing a statistician can do given a bunch of data, which is linear regression. So I switched the data set this week because the salary as a function of the rest of the parameters in the census example that we had, A, wouldn't be a very big predictor, and B, also the vast majority of those features were binary, so not a lot of interest there. So I switched to some really arbitrary data set from my perspective. It's called Communities and Crimes. It's one of the famous data sets that statisticians use to check various versions of statistical tools. If you want, you can look. This is how many rows we have, how many feature columns. Notice 33 feature columns relative to about 1,600 rows is still definitely within the regime where you can do linear regression, but not extremely easily. And dimensions, where the 33 is a dimension, are no longer negligible. We're not in the regime where it will take us minutes to run anything, but it's not negligible. And we know what linear regression is. We have a bunch of features, population, household size, race, if it's black or white, etc. All sorts of income per capita, whatever. Parameter. This is of a community. Like each row corresponds to some unit of area. I don't know if it's a zip code or whatever. And the label is how many violent crimes was per population. You want to predict what is the probability of a crime committed, that a crime will be committed in an area, or actually, to be more precise, is we want to predict how many crimes we expect to be committed within a certain amount of time. This is a relatively natural example for something that we will want to maintain its privacy, right? It is sensitive to some extent, whether it is that a row corresponds to a city, a household, a house, whatever. Like, obviously, we want to maintain. So, okay, we'll use that. Second thing, just to define settings. In this work, we will ignore the subtlety of range, both of x and of y. We will assume the norm of x, the features, is bounded by 1. So each vector of features, its L2 sensitivity, is bounded by 1. Why L2? Because we will mostly be using Gaussian noise. Had we been using mostly Laplace noise, so it will probably have L1. And the y value, the labels, is scaled to be within 0 to 1, or minus 1 to 1? No, 0 to 1, because it's non-negative. The way we did it in practice is I took the data set and I did the illegal thing of renormalizing to its range. again, for simplicity. In practice, we will need to have an initial stage where you privately estimate the range, etc., etc. The things that we discussed in the last week. This is, in a way, why we need to be able to privately estimate quantiles and moments and things like that. Because if we want to be able to work within a certain known scale, we need to know a few of these quantities. For simplicity, assume I learned it and I scale. In practice, I scale to the correct values. Okay. In case you don't remember, here's the definition of linear regression. We have a matrix X. Each row corresponds to an element. Number of rows is number of samples we had. That's about 16,000 that we saw. 1,600. Number of columns is number of features, 33. There's a vector of parameters, W, and the vector Y, which is 1 by this 1600, which is the feature that we want to, the label that we want to predict. And we're looking for a vector W that minimizes the L2 error. What is the solution? So, the classical solution, OLS, which stands for ordinary least squares or minimum square error, or it has a whole bunch of names, is taking the X matrix, X transpose X, that's a D by D matrix, inverse times X transpose Y. I'm sure everyone knows it, but just so we have it in mind, because we'll keep using it. Again, I'm sweeping a ton of things under the rug. Another thing I'm sweeping under the rug is the possibility that this matrix doesn't have an inverse. So we would assume that since the sample size is significantly larger than the dimension, we don't have truly degenerated dimensions. Maybe we will have dimensions where there's little variability, but nothing is truly degenerated. And another very common algorithm that people do in order to deal with the danger that there is a degenerated direction, which I don't care about that, but I will need it for other reasons, is the ridge regression, where basically did the same thing, but we added some value lambda, for some parameter lambda, to all the eigenvalues in a way. Momentarily we will see what do I mean by eigenvalues, etc. And then we definitely know we have a... Okay. So here's our data set, just so we have a sense of what's going on. So these are just a few values we can look at when we want to understand how well is a data set explainable by linear regression. So you have a 2D plot, which is the actual y versus the predicted y. Does it look like a perfect line? No. Is there a clear correlation? Yes. Good enough. What's the residual? There's some distribution of the residual. And this is the spectrum. So the spectrum of X transpose X is an important quantity, and it means the following thing. We will see momentarily. X transpose X has nothing to do with the label. This is so when we do linear regression, our story is that there is a distribution of features, right? Like the distribution of communities. How many of them have this population size and this average number of people in per household and portion of black people, etc., etc. That's one distribution. And then for any X, for any specific community, a specific vector of features that defines a community, there's a distribution of Y, which is sometimes you assume that it is like just the linear predictor plus noise, maybe it's some other function, etc. So the spectrum of X transpose X asks the following thing. If I take X transpose X, I have a covariance matrix. I have a positive semi-definite matrix, and we would assume that it's positive definite. What do I mean by positive semi-definite? It means that if I multiply from two sides by the same vector, I would get a non-negative, or if it's positive, so even positive value. In practice, what it means, it's a symmetric matrix, which obviously, because I multiplied X by itself, it is all of the values are real. We don't have imaginary communities, thanks God. And it doesn't have, it's not degenerated, therefore it is not semi-definite but definite. What are these values? They tell us the following thing. If I have such a matrix, I can think of it as the covariance of the distribution. So imagine, it's not guaranteed, but imagine the data of X, not the Y, came from a Gaussian with some mean and some covariance. So this would be a good approximation of that covariance, which is basically how are the features distributed. And it might be that it's independent and therefore the coordinates, the sort of the ellipsoid that describes the distribution is aligned with the axes. It might be diagonal. It might be the same in all directions. It might be not, right? Like the variability of different features might be different. So if you have a feature where nearly all communities have a very similar number of people per household, so that feature can't have a strong predictive power because everyone is 2.7. So it doesn't matter what weight will the linear regression put in that number. It's effectively like adding a constant. If there's a large variability, then that can hold a lot of signal. So the directions can be expressed basically by the eigenvalues of this matrix, and this is basically how they decay. What is important is you see there are a few that are very strong and a few that are very weak, which is not surprising. There are many typical ways of decay. Most real data doesn't have the same significance in all directions, that all of the features are well distributed as each other. Some are more important, some are more rich and some are less. Notice this has nothing to do with how well does it predict Y. This is the property of the distribution of X. Regardless of what you're trying to predict, the average salary per person or the number of crimes or number of babies that will be born next year, this is going to be the same quantity. This just tells me how many features have a lot of variability, little variability, which ones are they, in which direction. Then another question is, what does the signal have to do with it? Okay, so this is just a data set. A big part of what I'll try to do today is give a very visual intuition to what exactly are these quantities, what do they mean. So let's start with the most basic option. So assume I have a bunch of points. X is now one-dimensional. It's literally the x-axis. Y is just the y-axis. The points here sit perfectly on some line. So if I do linear regression, of course, it will be exactly that line. Now, if I moved one of the points, the red point in this example, the big one, so the line will slightly shift. Like in each of these are two data sets. Right? They change by a single element. Of course, the optimal line, the one that minimizes the square error, like, I'm not surprising anyone. Okay. So now we will want to discuss, okay, how do I do it in a private manner? What is the maximal effect of an element, etc. So first we need to define what do we mean by neighboring data sets and what do we mean by the privacy unit. So the privacy unit is always changing one element, and then there's the question of what does that one element correspond to. But it also is related to the question, what do we know and what we don't know? So when you have, let's say, mean estimation, so just like there's that value of that element, and you either remove it or not, or replace it by one else. But once it's something of the form of regression or some prediction task, there's the features and there's the label. And in some cases, the features are something that's known and the label is a thing that we need to privatize. So for example, we want to know based on some parameters of the person what is the chance that he will be a criminal or murder someone or I don't know, default on his loan or whatever. So the features maybe are public. It's okay. Yeah, people know what my height is, how many years of education I have, etc. But what I don't want people to know is whether I committed a crime or not. So that label DP. And then you have full DP, we will call it here element DP, which is like the full element. So the first option is I keep the X, I only change the Y. Other one is I change the X. I don't think label DP is very interesting for various reasons. There's also a limited amount of interesting work on it, though in some cases it makes a lot of sense to use that notion. I'm using it here mostly as a intermediate step of explaining what's going on. Okay, so here we have a point. The bigger point is the one that I can move. Okay, the green lines, which correspond to the dashed line, are the regression if I don't have the point. And now I can move the point and see what it does. And as you can see, not surprising, it changes somewhat the value. Okay. Now, here's the question. What in the setting determines how much did the line move as a result of my movement of the point? For example, can you come up with some change to the setting such that if I will move this point about the same amount, notice by the way it's moving only up and down because for now it's labeled DP, so its X is fixed and I'm only playing with Y. Can you come up with a setting where I move it about the same amount and the line would move by a more significant, will have a bigger influence on the line?
How close you were in the first place.
Sorry?
That's how close you were in the first place.
I'm moving. Sorry, I'm going to make this move in both cases. Here I did one sweep, and you saw the movement of the red line. Now propose some change to the setting. I'm not changing this point. This point will move exactly this amount, but the rest you can do whatever you want.
And you can change the data too.
Yes, the rest of the data you're welcome to change.
X values or X are all clustered on the same point, basically. Then you just change the whole one.
I have a lot more. Okay, exactly. This quantity is called leverage. We will see a bit later what exactly does leverage correspond to. But here's the example. I just clustered them just a little more. Or another way to look at it is I moved the point a bit further. And now, as you see, the change is bigger. Why is that? It's because there is a direction in which this point shouts louder than the rest. Now, what is the direction here? Here there's only one direction because there's one feature. But all of the features have a certain scale, and this point is further away, so its vote is stronger, especially because this is in linear regression, this is a square loss. So as you go further and further away, your effect is much more significant. That's why linear regression is very sensitive to outliers. One crazy outlier can completely push you away. So here, now, this is not an outlier, right? It matches everything perfectly, but now it is an outlier, and unfortunately, one outlier can have a big effect. Okay, so we already see that this is a much more complex setting than what we saw before. Now there's a lot of interaction between the data and the element and what kind of choice, etc. So we're no longer in a world where we can make easy changes. Okay, so what can we do? Proposals. How can we privatize it? Again, just reminder, rules of the game, only two assumptions that you have, three pieces of information you have. You know the sample size. I'm going back and forth between add, remove, or replacement, but okay, I'm replacing by a 0 or whatever. So you know sample size, you know the bound and the norm of x. For simplicity, let's assume it's 1. You know the bound and the value of y. For simplicity, let's assume it's between -1 or 1, or in the real example, it's between 0 and 1. These are the rules of the game. What can you propose?
We can take different subsets of the data
and to train different model on each one of the subset and to do like an ensemble of all of them together. Then maybe one outlier won't affect more than one or two models.
So A, great idea. Basically what Shai is saying, if we split the data into subsets, and we expect, if our sample size is reasonable, each of them to have like a reasonably good model, then most of the models will sort of agree. One of them at most will change by changing, or two if you, but let's say one, because like that model maybe I change the element, but still it's one, and then I'll do some kind of, vote and identify it. First of all, what kind of algorithm that you're already familiar with does this falls into a known category?
Subsample and aggregate.
That's subsample and aggregate, exactly. And as is the case with all subsample and aggregate, you're basically pushing the problem down the line, right? Because you're saying, oh, I'll do the estimation in a non-private manner. Oh, my life is great. Now I'll only have to aggregate in a private manner. Okay. If you're aggregating a number, let's say it's subsample and aggregate over estimation of the mean or the median or something like that, some single number statistic, well, okay, cool, I have a bunch of numbers and now I want to privately release, something that's in the middle of the bunch, and I do private median estimation, private mean estimation, report noisy max if it's a finite number of, let's say, labels. But here you have a d-dimensional quantity. It's not so clear how to do it. And you would pay something that scales with d. So d being the dimension, I don't get it doesn't matter exactly what exactly does it scale to, but give or take the number of features. And it will work, and generally you will now need a sample size that's about d squared. Why? Because each subset has to be about order of d in order to be able to get the non-private estimator. D, effective d, right, sometimes if it's low. And then you need d of those at least in order to have an aggregation in high dimension that is private. So you have a significant degradation with the dimension. But it's definitely a valid and one of the first algorithms that were proposed. But that's already relatively sophisticated. Okay, on one hand, it's the least sophisticated thing. Where I don't want to produce a private algorithm. I'll do it in a non-private manner, and I'll just aggregate in a private manner. Typically, subsample and aggregate will solve your problem. Typically, it won't be the most efficient, not only by constants, in many cases by some asymptotic quantities. What is sort of another very simple step we can make?
Use kind of prior on the data that say
No priors. That will be out of the rules of the game. Though, again, a bit like last week when we said, public data can help us to start making better guesses. Absolutely, a ton of things. We can just try to privatize the actual input. This is called input perturbation, and that is something you should always consider when thinking about private learning or estimating of any kind. If I can take the point itself and add enough noise to privatize it, this is basically local DP in a way. So the element itself is already private, and everything coming after it is post-processing. Okay, so I can always do this. Every point, like again, here the points were on the line, and I sampled some randomness. Again, still only in the y-axis because we're in label DP. And I got a different one. I will sample again, I'll get a different one. Right? A whole bunch of those. When you look at it, it's like, right, this is the dashed line is the true one, and you have a whole bunch of alternatives. It's going to be noisy to some extent. What is the main problem with this type of setting? So how much do I need to add noise? What does it need to scale with?
The number of elements. every element needs its own noise.
Yes, but it's not like every element gets more noise as the number of elements
Yeah.
grows.
No, the total noise scales with the number of
Right?
elements.
So the actual effect actually decreases because it's basically NIID sources of noise, so it scales only with the square root of n. But yes, so maybe another way to say it is each element has an amount of noise added to it that doesn't decrease with the sample size. That is what happens in local DP. So yes, when I add a whole bunch of elements, each one got IID noise, the total amount of noise, the effect is smaller, but each one got a significant amount of noise that I can't decrease as the number of samples grows. And that amount of noise scaled with the range of y. Now, imagine you have a linear regression setting where the range of y is huge, but the prediction is very good. So now you will have to add noise that scales with the range of y, even though the actual variability, the natural noise in the distribution is much smaller. So it's typically
Probability
not.
estimate the distribution.
Sorry.
Probability estimate the distribution to decide how much noise to add.
So that's for sure. You can be practically certain that estimating the distribution is much harder than estimating the regression. But I will say that mean estimation, covariance estimation, subspace estimation, PCA, principal component analysis, and linear regression and high dimension, these are all very strongly intertwined. We have a whole bunch of reductions. Reductions in the sense that once you know to do this, you can do that much more efficiently in runtime, sample size, etc. And also we now know that half of them are sort of the same thing. So I can already tell you that linear regression is as hard, give or take. I'm really simplifying things, but give or take as estimating the covariance of the data. So you didn't get away.
Maybe make it more precise by first calculating it with noise scaling to the range, and then, now we have a much smaller range.
So that is exactly what we did last week. Basically what you are proposing now is another variant of the coin purse algorithm, right? Which I mentioned, which was we estimated the mean, the variance, we used it to do clipping, and then we estimated the mean again, or we could have done it a few times. Yes, all of these algorithms, all of these statistical tests, if you have an initial bound, so you can start with something, you can always do this coin press attitude. Theoretically, typically you can't prove that it's not going to be terrible because I can find distributions where you're going to be really off and you're going to pay a lot of error as you get closer to a good estimation. And practice, sometimes it's better, sometimes it's worse. That is already in our toolkit. We don't need to. It's the same way in a way as the subsample and aggregate. We can always use that. But I'm looking for things that are a bit more specific to linear regression. Okay, now let's go to element DP, which will look almost the same, but as you'll see, now the effect of the noise might be even a bit more annoying. Okay, so again, I have a point. Now I can move it not only this way but also this way, and you see there's like different effects. And again, if my leverage is larger, that is, the element is more unique relative to the point, now I can do like really crazy things. Okay? Now adding noise, again, I can still do private input perturbation. Input perturbation now just needs to perturb the x's and the y's as well. And now you can see it's a bit more crazy. And part of the reason it's a bit more crazy is now if your x's are not sufficiently spread out, then you can also have like another sort of direction in which things go crazy, and you see the effect is bigger. I can quantify it, but we'll get to it later in a more intuitive way. So input perturbation has the problem that you need to add noise that scales with the entire y, but also that if your x is somewhat close to degenerated, then the noise you add there has a much bigger effect. Okay. Yeah, and we have here some distribution. Actually, I don't think it even matters. Yeah, I don't think we should even look at it. Okay. Another option. Output perturbation. You should also consider that as like your second or first guess. If I can either perturb the input, or I'll do the entire algorithm as usual, and then add noise to the final model. How much noise should I add? Well, that should scale with the sensitivity. So in this case, this is a short discussion. Why? Because there is no way to bound the sensitivity of linear regression to a change of one element in the general case, right? The example Nissan mentioned before, if I take that small leverage and take it to the extreme, all the points are really close to each other, one point is really crazy far away, I can arbitrarily change the model, so the sensitivity is practically infinite. I'll need to uniformly sample a point. But I do want you to remember it, because we will meet examples in later stages where output perturbation is also a good option. So, besides the fact that we just encountered two options, besides the fact that we encountered one option that works and one option that doesn't work to do private linear regression, I want you to remember these 2 points as also like the first two things that come in mind when someone proposes, when someone discusses some learning statistical estimation task in a private manner. And there's like 1.5 other methods that we will consider now that are also should be considered, typically result in better privacy utility trade-off, typically are harder to do. Because like input perturbation is very clear, like you know what if you have boundary range, etc., you always local DP. Output perturbation is either very clear or doesn't work typically, right? Because you just ask, well, what is the sensitivity of this model to changing one element? Either I can bound it, then I'll add noise with that. Maybe good idea, maybe bad idea, but it's very clear what it does. Or I can't bound it, and then there's nothing I can do. And then will come the more complicated things. Okay. So now I'm trying to go up one dimension, because this is the minimal number of dimensions where we can start understand what richness is. So Shachar, first question, is the color gradient here clear? Okay, good. So how should we interpret this? This is what's happening here. Now there's x1 and x2, and the color intensity corresponds to y. This is the regression. So we'll see it in a moment in 3D, but basically this is a heat map corresponding to some hyperplane, right? It's higher here and lower here. And how do we know that this is the correct model? Because we have these points, and each of these points has some value y. It's a bit harder to see here that there's also some color gradient. And therefore, if we fit a plane, right? Because these are like points popping out of the board. If we fit a plane to it, it will look like this. This is the setting here. Why did I move to the third dimension? Because now we immediately see that there are two types of distributions here. One is the distribution of the points on the plane. This, what we see here, if you ignore colors for a moment, this is the distribution of the features. That's what X transpose X represents. Right? This would look the same regardless of what is the function y given X. For any plane that we would have here, this would look the same. Only the colors will change. Okay? So the X transpose X corresponds to where are the points located here, and the y tells me something about what is the color gradient. And this is going to be important because these are the two different quantities that govern how linear regression is done. We will partially better understand linear regression because we need to think hard about these subtleties and how we can do privacy. Okay, so let's see what's going on. So now we have a third dimension point. Let's just see. Here we're looking at a top view, so we can see this is a distribution, right? This corresponds. This is sort of like a Gaussian-ish, like how the mainly spread across the first coordinate. When I said before this, when I mentioned the spectrum, I said there are different eigenvalues. Now we can see it. This is the first eigenvector, which in this case is just the x1 axis. This is the second one, and we can see here the variance is much larger. So this corresponds to a larger eigenvalue. Okay? There's more variability in the x1 axis versus the x2 axis. Okay. This still tells me nothing about how y behaves as a function of x. So, in this case, there's some slope. This is a function of x1, nearly or perfectly linear in x1. These are two separate things. Okay. Now, I'm going to start changing the point, and I'll see what happens. So, first, let's change the y value of the point. Okay, so now I'm moving it up and down. Sorry, wait. I want to have it in. Okay. Gee, that's not good. Didn't move before. Let's see if I can do it now.
Actually, what actually helps is if the plane itself was in multiple colors, right?
No, I think before it didn't flip back to the starting point every time I moved something. So okay, good. So you see now I put the point, give or take, at the middle of the distribution, right? You can look at it from above. We can see it, right? It's just in the middle. So when I'm changing its y, it doesn't have a significant effect on the plane because it's clearly an outlier. It can't be better explained by the plane without ruining everything else. So this is a very low sensitive point. But if I were to move its location, again looking now from this perspective, okay, so I'm asking where can I move it so that it will have a bigger effect when I change its y value. Right? Here are the rules of the game. I'm going to play with the y value as much as I'm allowed. Let's say plus minus 1. So now the question is which x will mean this point has a significant effect and which one means it doesn't. Okay, so clearly if it's in the center of the whole cluster, the rest of the points yell louder than it. So it can't do anything significant. It has to move away. But in which direction? So give me a guess. Is it in the x1 direction, which is where most of the points are spread, or in the x2 direction? Where do I get more bang for the buck? If I change it, if I move it by 0.2, where do I get a bigger effect?
X2.
Sorry?
X2.
Why?
Because everything else is basically degenerate in that dimension, so they don't care about that specific.
Exactly. In a way, what Nissan says, if I'm moving the red point further away in this direction, there's still a lot of signal in that direction from the other points. So even if it's an outlier, the other ones say something else, so it has to be something in between. It's sort of back to the one-dimensional case. But in the other direction, that's the only one saying anything about it. Like all of these are nearly oblivious to changes in that direction. So let's try to do it. Yeah, okay, let's see here. I moved it now in the x-axis.
X1 equals 0.
So,
west of here.
right, but it's just, again, as I said, this is not fully stable. So you see, I moved it significantly in the x-axis, like by more than 1, and it is changing the model, but not by much. But if I move it, if I put it here back to about 0, and I move it here by, let's say, I don't know, just 0.2, now this is crazy how much it changes. Okay, so what it tells me is that, when I look back here, now I understand where will a point that has a significant influence be located. Where? In this direction. So the further away it is, the bigger the effect, and the further away in the most degenerated direction. There is a formal quantity to it, which is called leverage, and that is exactly the Mahalanobis norm. Mahalanobis norm is, if you take the vector inner product with itself with the matrix in the middle of the vector, which is the minimal eigenvalue, and the norm in the Mahalanobis matrix is the inverse of the x transpose x, which is basically you take a vector of whatever range you bounded and you divide it. It's the range squared divided by the minimal eigenvalue. This is the quantity. But for our intents and purposes, I don't care that much about the equation because it's not like I'm focusing on defining the exact algorithm, though I will mention what it is. What matters is the intuition of what happens here. There are directions that are more degenerated. In those directions, one element might have a more significant effect. And therefore, in the general case, sensitivity is really unbounded. Okay, so here we can just see what would it look like. So this is now input perturbation in 2 dimension. I mean, nothing is surprising. There's one plane that's not changing. That is the true one, and the rest are sort of shaking. And this is what it looks like. Not the most intuitive thing, but again, it's like what happens is the same thing. And again, it's hard to show, and maybe I'll figure out a better way to do it. But you know that there's one direction in which the planes didn't shake by much, and there's another one where it shaked more because that is the degenerated that is the degenerated setting. Okay, let's see if I want to cover this. Sorry. No, okay. Just an explanation. Here, this ellipsoid, this is going to be part of our language, so I'll already introduce it now. This ellipsoid corresponds to the covariance matrix. How does it correspond to the covariance matrix? So, again, as I said, we can think of the covariance matrix as though it's the covariance of a Gaussian distribution, just for ease of intuition. And in Gaussian, you can, if we draw the contour lines, the line that has some fixed probability density function per point. So in 2 dimension it's an ellipse, and in high dimension it's an ellipsoid. The directions of the ellipsoid, its axes are the axes of the covariance matrix, are the eigenvectors. The width along each direction is the eigenvalues, right? So this is the x1 in our previous example. I mean, now it might be, it is still the x1, it's the same one. You see, because here this is axis aligned. Could have been rotated in a different way, right? So I'll just show it. Here we see it, here we look at x1 and x2 just as a top view. Now we don't care about the regression. And you see there's just, this is sort of a Gaussian. And I mean, these points might have actually been sampled from a Gaussian, maybe from something else, but like had it been a Gaussian, this is what its ellipse would be. And this basically is the way to notice that, there's one direction that is more degenerated than the other. Okay? And here we have an example where you see it's better spread, and therefore the ellipse is closer to a circle, so you would see for the same amount of noise on the y-axis, the amount that the plane changes is a bit less significant. There's no big surprises here. So, before we leave to a break, let's recap what we figured out so far. So in linear regression, what we have basically is distribution of features and then the distribution of y given the features. In the general case, one point can arbitrarily change everything. And how strong is its change? So first, there is the question of how much of a voice does this point have, which corresponds to how big is its norm, effectively, how far it is from the center, and in which direction does it point. The further away it points, and the more it points in the most degenerated direction, the stronger its voice is. Still, that doesn't mean it will change the model by much, because maybe the y-axis will perfectly match the model from the other points. But once that point has a stronger voice, then for the same amount of change in y, it can change the value of the final model by more. The first one, the how much voice does it have, is called leverage. The second one, which is how different is the y it provides relative to the model of the rest, is called residual, unsurprisingly. And these two quantities were developed in the context of statistics, mostly in robust statistics, which was how do I mitigate the effect of a single rogue element. And this is again an example to something we're starting to see more and more throughout this course, which is that things that people cared about for years in the context of robustness and generalization and all sorts of other reasons where people didn't want one element to have too much of an influence, all of a sudden pop up again in privacy. And in a way, what we will figure out and find out in a few lectures is also now privacy somewhat contributes back, because I believe that asking the question of sensitivity for the privacy purpose is a very useful tool to understand what do we do when we learn, even if we don't care about privacy, and we will see more examples later. Okay, so let's have a break.